Okay, Matt Roscoe here at the University of Montana, and a continuation of our treatment of Chapter 10 from um, Burton's text on on history of mathematics. We're going to talk a little bit more about number theory and the revival of number theory during the Renaissance, and on this video, particularly Mersenne and Fermat's contributions to number theory. So we talked a bit about the rise of scientific societies in class. We talked about Mersenne, who was actually a priest in France who offered his monastery as a location for regular meetings and the exchange of ideas. He was particularly interested in these objects called perfect numbers, and a perfect number is any number where the sum of all of its divisors sum to twice the number's value. Another way to put this is all of its proper divisors, that's its divisors accepting itself, um, equal the number itself. So the first perfect number is 6. Its divisors are 1, 2, and 3, so those sum to 6. The second perfect number turns out to be 28. The third perfect number, 496. The fourth perfect number, 8,128. And the fifth perfect number, 33,550,336. And the sixth perfect number, 8,589,869,056. So it turns out that the first four were known to the ancient Greeks, but it took some time for us to find these others. And as you can see by the list, these are fairly rare types of numbers in our numbers set, or I guess in the integers. And so it makes sense that these are something that would drive the development of number theory, the search for perfect numbers. So we took some time and proved this statement, and so it turns out that since antiquity we've known how to generate perfect numbers if we can find primes of the form 2k minus 1. Because if 2 to the k minus 1 is prime, then the number n equal to 2 raised to the k minus 1 times the factor 2 to the k minus 1 is a perfect number. So we went ahead and proved that, and we used this little lemma to prove it. The lemma, of course, provides that any factor of a number is some subset of that number's prime factorization. But here's where we got to in class. Euclid's theorem on perfect numbers gives rise to the question for what integer values of n is this number 2 to the n minus 1 a prime. So we call these numbers of the form 2 to the n minus 1 Mersenne numbers after Mersenne, who intensely studied them, and if the number is prime, it's called a Mersenne prime. So interestingly, Mersenne, we're talking about in the early 1600s, claimed that he had found them all up to 257. So he claimed that for p equal to 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, and 257, that m of p, that is 2 raised to each of these exponents minus 1, or each of these numbers, each of these primes as an exponent, minus 1, that each of those were prime, and all the other Mersenne numbers in between were composite, at least those that were less than 257. And it would take 300 years to verify or correct this claim, for it was not necessarily correct. And you can imagine these are huge numbers when we're talking about the end of the list here. 2 to the 127th power minus 1, 2 to the 257th power minus 1. So in a time when there were no computers or calculators, it's unlikely that Mersenne actually calculated any of these numbers, and how he made this conjecture is uncertain. But let's tell the rest of the story after we take a look at some of the Mersenne primes here. So I'll put us in split screen, and so I have this Excel file which calculates all the Mersenne numbers, and if we take a look at the list n, so here I have the integers. First it tests that list for primality, so you can see 2 and 3 come up as prime, 4 is not prime. And then of course here is the Mersenne number calculated for each of those n, 2 to the n minus 1, and that's the result. So you can see that when n is prime and is 2, we get a Mersenne number, the second Mersenne number, which is prime. When n is prime and 3, then we get the third Mersenne number, and it's also prime. And when n is 4, we get the fourth Mersenne number. It's not prime, and neither is n. And so it looks at first glance that whenever n is prime, the Mersenne number is also prime. But we do see that right away we get the first case right here of a non-prime. So when n is 11, 2 to the 11th minus 1 turns out to be 2047, and it's not prime. And as you can see, Mersenne was aware of that. He didn't include 11 in his conjecture here. And interestingly, it's the first prime he skips over. Neither does he include, well, let's say 19. So there is some question about whether, oh, he does include 19, I'm sorry, but 23, for example, is not included as a prime. So we can see that it looks like it's necessary for n to be prime in order for a Mersenne number to be potentially prime, but not sufficient. And it turns out that he was also correct on 23, that 23 is actually a non-prime. Here we have a 7-digit number, and try to factor that one into its prime factors. This would be an interesting question, how he knew that 23, for example, was non-prime. But we quickly run out of machine. Well, I guess we can see that 29 also is a non-prime, and 31 is included in prime, a very large number. And when we get to 37, we see a non-prime as well, not included in the list. But at some point, here it is, at about 41, we run out of machine precision in Excel. These are extremely large numbers now, on the order of 12 to 13 digits, once we're out to 2 to the 39th. And so the computer can no longer check division. And so it's some question, if the computer, for example, can't do it, how Mersenne came up with this conjecture. So that's the story. Let's tell the rest of it. It turns out that within the lifetime of Mersenne, we find Cataldi, who shows that m of 19 is prime. And so indeed m of 19 is prime, and the 7th perfect number is found. Euler verifies that M31 is prime, and the 8th perfect number is found. Lucas shows that M67 is composite, and he gets a standing ovation for this demonstration. This is a number way down in our list here, of course. It's about a 20-digit number, 21-digit number, and he's able to prove that it is composite. He gets a standing ovation by the Royal Academy. It's a really interesting story. I hope that you'll read it. Both Pervusian and Seelhoff in around 1886 show that M61 is actually prime. So that's, I guess, right in here. We know that this one is actually prime now. This is an 19-digit number. In 1911, Powers shows that M89 is prime. Recall that Mersenne did not include 89 in his list, so this was an error of omission. And he also showed in 1917, Powers showed that M107 is also prime, also not in the list of Mersenne. And finally, in 1922, we find that M257 is actually composite, and Cratchit shows that. Of course, it was Mersenne who said that 257 was prime. So one last word on Mersenne. We know that right now, as of March 2018, the largest known prime is this number, M77,232,917, which is, of course, the 2 raised to that power minus 1. It's a number with 23 million digits, and it was found by the Great Internet Prime Search in late 2017. And of course, it's a Mersenne prime. Most of the largest primes that we found in the last 10 years have all been Mersenne. So let's move on and talk a little bit about Fermat. He was a French civil servant. He's known as the Prince of Amateurs, and perhaps the last great mathematician to pursue mathematics as a sideline pursuit to a non-scientific career. So he is a mathematical amateur, but was certainly a large contributor. The crux of the problem for perfect numbers is to ascertain which numbers of the form 2 to the n minus 1 are prime and which are not prime. And Fermat gave us one way to take a look at all of the numbers that are close, that can be considered in that light, and that's through his theorem, Fermat's little theorem, which says that if p is a prime and a is any integer, then a to the p minus a is divisible by p. takes a little bit to get used to what this really means, so let's take a look at what this means. So Fermat's little theorem, if I take the base A and I take, let's say, the prime 3, then Fermat's little theorem says that a raised to the p minus a should be divisible by p. So here I'm checking to see if it's actually divisible by p. So if I take 3 as my prime, the base is 2, then what we have 2 raised to the third minus 2. Well, that's 8 minus 2, or 6, and 6 is indeed divisible by 3. It's divisible by 3 because when divided by 3 it yields a quotient of 2. And you can see that this indeed happens when I change the base, the power to 5 or to 7 or to 13 or to 19, that every time we come up with an even divisor over here. But that's not all. If I change my base to 3, then it's going to work as well. If I say a is 3, then I have 3 raised to the third, that's 27, minus 3 is 24, and 24 is divisible by 3. It yields 8. And of course all of these quotients are all whole numbers, indicating that there is even division going on, at least up to the machine precision here. Of course, things are going to get rough if I pick something, big here. Say if I picked a composite number like 8, well then 8 raised to the third minus 8, looks like 8 raised to the third is going to be 512, minus 8 is 504. When I divide 504 by 3, it evenly goes in 168 times. Because of the scale and the exponential nature of the relationship, you can see that we run out of machine precision pretty quickly. Okay, well, let's go and see if we can review a little bit of a proof of this conjecture, I guess, or of this, not conjecture, but theorem. I'll put this over here, maybe. Well, here I have a short, I guess, written outline of Fermat's little theorem proof. This is something I would provide on the board if I was with you today, but maybe we could just review it. So what do we want to show? We want to show that p divides a to the p minus a when p is prime and a is a member of the positive integers. So how are we going to do that? We're going to break it into two cases. In case 1, what are we going to show? We're going to take the case when p is an even prime. So there's really only one case to analyze, and that's when p is 2. We know that to be the only even prime. And in that case, this a to the p minus a would be a squared minus a. And that's in factored form, a times a minus 1. And if we sort of think a bit about what we have here, well, a is some integer, so we have integer times integer minus 1. So that's the product of consecutive integers, right? A times a minus 1. So what does that mean? That means if this one's even, that one's odd, or if this one's odd, that one's even. So we can definitely say that 2 divides this always. And if 2 divides it, and 2 is our prime, then this is certainly true when p is equal to 2. Okay, let's take a look at case 2. In case 2, what do we have? Well, now we're talking about p being an odd prime. And here the idea is or the method is to induct on a. So we need a basis. We'll let a be equal to 1. Well, then if a is 1, this a to the p minus a is going to be 1 to the p minus 1. And 1 to the p, of course, is 1. 1 minus 1 is 0. And anything divides 0. So p will certainly divide 0. We have a basis. So what do? We go ahead and we assume that the statement is true for all a, and what we need to show is that it's true for the next a, so to a plus 1 here. Let's go ahead and look at just this little term here, the a plus 1 raised to the p. And by the binomial theorem, we can expand this, right? We can say, well, that's just a to the p times p choose p choose 0. I think I have that wrong, don't I? Yeah, that's p choose 1. P choose 0 would be the coefficient on this one. So let's do p choose 1. Sorry. And p choose 2. So p choose 1, a to the p minus 1. P choose 2, a to the p minus 2. And so on until we get to p choose p minus 1a. and then p choose p, which is just 1, times a to the 0, which would be just 1. So if I take these two terms, the ones that are underlined here and here, and I move them to the left-hand side over there, what I get is this, and what I get on this right-hand side is this. So it's sort of like the expanded polynomial missing its leading term and its tailing term. And there is a little lemma that we need to employ right here, but I think you'll believe me. I know I need to correct this as well. That should be p choose 1 and p choose 2. Right. Here, I think you can see that each one of these is going to have some combinatorial combination expansion, and in each of the combination expansions of each of these, what we're going to see is that it includes a factor of p. So p will divide this term, and this term, and every term in between. There is a lemma for this that says p divides p, choose k, when k is 1, 2, 3, and so on. So if p divides this side, then p certainly divides this side, right? That's the fundamental theorem of arithmetic that allows us to conclude that. So p is definitely going to divide this side. That's this term right here. We can also use our induction hypothesis, which is up here. And so p also divides a to the p minus a. So if it divides both of these, then it certainly will divide their sum. So what happens when I add these together? Well, when I add these together, the a to the p's will cancel, and I'll get a minus a minus 1, which I could factor out the minus, and we would have p dividing the sum, which is exactly what we set out to prove. So by the principle of mathematical induction, we can say that p must divide a to the p minus a for all a in the set 1, 2, 3, and so on, and p when p is odd. So since case 1 is true and case 2 is true, the statement is proven for all primes and all a element of the positive integers. I'll scan this and make sure that you get a copy. But let's talk just briefly about what it means. From Fermat, we know that p divides a to the p minus a. If we factor out an a, there it is, and then let a be equal to 2, because of course this statement is true for all a, then what we get is that p divides 2 times parentheses 2 raised to the p minus 1 minus 1. And of course, this guy is some sort of Mersenne number, p minus 1. So if p is not equal to 2, and you can rule out the 2 case, then we can conclude that p will divide the other piece, right? If it doesn't divide this, it's got to divide this one if it divides the product. And so if p divides this, what that tells us is that Mersenne numbers, whose indices are p minus 1 for some prime, are all composite. And so basically Fermat's theorem allows us to eliminate a certain number of numbers that could that are composite in terms of Mersenne primes. So one last note on Fermat. Fermat's probably most famous for what he wrote in the margin of his copy of Diophantus's Arithmetica. He said it was impossible to write a cube as a sum of two cubes, a fourth power is the sum of two fourth powers, and in general any power beyond the second as a sum of two similar powers. For this I've discovered a truly wonderful proof, but the margin is too small to contain it. And of course this is the theorem that bears the name Fermat's last theorem, that would become one of the most, I guess, sought after theorems in mathematics. Basically, you can think of it this way, that we can find integers that satisfy Pythagoras' equation, a squared plus b squared equals c squared, but we can't find integers to satisfy any analog to that equation when the exponent is raised to 3 or 4 or 5 or any power beyond the second. So there is no Pythagorean triples when, I guess, or I guess there are no three numbers when we raise the exponent from 2 to 3 in a setting similar to Pythagoras. And this particular theorem, of course, took several hundred years. We just got a proof of it in the late 90s. So probably what he's most well known for, of course, was his last theorem, which Nobody is quite sure whether he really had a truly wonderful proof, but most experts agree that he probably was mistaken given the difficulty that the proof um, gave mathematicians for a complete proof. All right, well, that's all for Fermat right now. Watch for another video coming for the rest of Chapter 10.